Okay, so welcome to the 12th video in the Discrete Structures series, and this video is going to be about modular arithmetic. And we discussed this in a little bit in the 7th part of our series, but we're going to go into the depths of it here. And that will include defining the Congruence Modulo Notation and also look into the idea of Congruence Classes. And then we'll look into a couple of theorems on modular arithmetic. And here is an overview of that. And next we're going to look into a couple of applications of modular arithmetic. And specifically, we'll be looking at hashing functions and pseudorandom numbers. Okay, so that is the overview. Now let's dive into our first topic. So a few details on the basics of modular arithmetic. And before providing any definition, I just want to give you a very basic example. So imagine this circle is representing a 24-hour period of a day. And imagine currently we are at this 8th hour of the day. Okay, so it's currently 8 a.m. And I want to bring ahead a very simple question. What is going to be the time 22 hours from now? And I can see that in 24 hours, it's going to be 8 a.m. tomorrow. Therefore, in 22 hours, it's going to be 6 a.m. in the morning. But how can I define this in terms of mathematical operations? See, the question simply states that the current hour is 8, and what time would it be 22 hours from now, right? So it would simply be 8 plus 22. So the result is 30, but 30 isn't even a valid hour, right? So what I'm forced to do, technically speaking, is to take a remainder of dividing 30 by 24, right? And I want to take a remainder of this process. I don't want to actually divide, but I want to take the remainder. And that is going to give me the 6 that I'm looking for. Because 24 times 1 is 24, and that leaves 6 for a remainder. Okay, so my initial time of 8 a.m., when I'm adding 22, I'm getting to 6 a.m. And if I add one more batch of 24, which is my cycle period, I'm still gonna get a 6 a.m. So if I take a sum of these two, and that's gonna be 46, it would be correct to say that if the current time is 8 a.m., the time that's gonna be after 22 hours is gonna be the same time as 46 hours. So inside the domain of this cycle of 24 hours, 22 and 46 are kind of like the same. And in fact, this pattern turns up so many times in practice that we have a special notation for this. And the notation is called the Congruence Modulo Notation. So we want to say that 22 is the same as 46. Okay, so we do that by saying 22 is the same as 46, or this is rather called congruent. And you'd notice this is not always true. This is only true within my domain of 24 hours, right? The number that I'm dividing by. So therefore I have to mention this is mod 24. And essentially all this means is that 22 and 46, when divided by 24, leave the same remainder. So to formalize this a little bit, if I write A is congruent to B mod M. So if we think about it, A when divided by M leaves some remainder, and B also leaves the same remainder when divided by the same M. And how can we express that? So let me start by writing A is a multiple of M, okay? Although it's not true, I'll write A equals M times some constant K. But there is a remainder. M times K is not exactly A, but it leaves a remainder of R. And it is true because M does not exactly divide A. But if I subtract the remainder from A, you could imagine this R being transposed over this side with a negative sign, and that A minus R would be an exact multiple of M, right? K times. And this fact would also be true for B. I could also write that B equals M times some constant K plus the same remainder, although these constants would be different. And this gives me a relationship between A and B. I can subtract these equations to obtain A minus B equals M times K1 minus K2. Okay, and since K1 and K2 were arbitrary constants, I could just replace it with a single constant, and I could say A equals B plus some K times M. Okay, and this is going to be my mantra. Every time I see A congruent to B modulo M, I'll transpose that into this expression. A equals B plus some constant times M. Okay, and there's an alternative way to say the same thing. I can say from here that A minus B equals K times M, right? So a constant integer times M. And that would lead me to imply that M divides A minus B. The modulo factor would always divide the difference between whatever are congruent. I could also make sense of that with a little thought. Because A and B are leaving the same remainder when divided by M, And therefore, when I subtract them, the remainder factor cancels out, right? So whatever remains would be an exact multiple of m. Next, we'll look at a couple of theorems. But before that, let's look at this terminology called congruence classes. And this is quite basic actually. So let's say I'm asserting that 12 is congruent to 17 and mod 5, okay? 12 when divided by 5 leaves some remainder, that is 2, and 17 leaves the same remainder. So if I fix one of the numbers, let's say if I fix 12, I can come up with a range of other numbers that are always congruent to 12 mod 5, right? Because 22, let's say, also leaves the same remainder. So does 27 and 32 and 37 and so on. So all of these numbers form the congruence class of 12 mod 5. So the congruence class of A mod m can be defined as the set of all B's for which A is congruent to B mod m. So this is just a terminology to be careful about. Okay, so next let's have a look at a couple of theorems under modular arithmetic and the congruence modulo notation. Okay, it is given that A is congruent to B mod m, and it is also given that C is congruent to D mod m. Okay, and it is asked of me to prove that A plus C is congruent to B plus D under the same modulus m, and also the product AC is congruent to BD mod m. And it kind of states that the properties of congruence are maintained under addition as well as multiplication. So I'll do one of these in this video and I'll leave you guys to do the next one. And this initial part is going to be common for both the solutions. So A congruent to B mod m, I'm going to transpose that into A equals m times some constant k plus B. And I can transpose this one similarly. I could write C equals m times some constant k plus D. And these constants again should be different here. And then you look into the end result, right? So I want to achieve this result. So therefore I go on adding these things. When you do this problem, you probably want to multiply. Okay, so I'll get on to this side. So if I add these equations, I get this equals m times k1 plus k2 plus b plus d. And again, these being the sum of two constants is also a constant. Then I could say a plus c equals m times some constant k plus b plus d, right? And this is the same pattern as this. And this would allow me to say a plus c is congruent to b plus d under the modulus m, right? Because it's still m in here. Okay, so I invite you to now multiply these two equations and come up with a relationship that proves that AC is also congruent to BD under mod m. Next, we'll look into a couple of applications of modular arithmetic. And we're going to look at hashing functions first. And next, we'll have a quick look at pseudorandom numbers. So hashing functions. Okay, so imagine you have a table with 10 labeled spots, 1 through 10. And you want to keep 10 books in here. So each book has a label from 1 to 10. And the question is, what is the optimal strategy to arrange these books? And this should be a fairly easy example. Since I have the books labeled from 1 to 10, I definitely don't want to store them randomly. I probably want to correlate the book number 1 with this spot, book number 2 with this spot. So if I place my first book here, second book here, and so on, later on the task of retrieving a book becomes much easier. So hashing essentially allows you to correlate object properties into actual locations. Okay, by looking into the book label itself, I could determine where I could find it. And what can I do here if the number of books could be more than 10? See, it's easy to get confused here. The question is not about being able to store more than 10 books, but it is about being able to manage a wider range of books that could potentially arrive. Okay, so let's say I'm only going to give you 10 books, no more than that. But the labels can be anything between 1 and 100, okay? And how would you organize 10 random books whose labels could vary within this range? So basically, I'm asking you to design a hashing function. And there is a very primitive and common hashing function that just works on the basis of modulus. So in this case, I could say whatever the book number is, just divide it by 10 and then take the remainder. Okay, and that would be one way to hash this space of input books. And my hash function would look like a function of the book number, and this would just be n mod 10. So if I get book number 57, for example, it would just go to the 7th spot. And you could immediately notice a problem with this approach. If I receive book number 67, it's also going to have to go to the same spot. So this hash function in our jargon is not 1-to-1. Okay? And this situation, when two inputs get hashed for the same output, is called a hash collision. So this is a very common hashing example, and this is not used at all, but this should provide ideas about learning the concepts of hashing and the general ideas relating to it. Next, we move at the last section of our video and a quick discussion about pseudorandom numbers. So pseudo-random numbers. Okay, and let's discuss a little bit about the concept of randomness. What does random actually mean? So let me ask you to think of a completely random number, and I'll do it myself. Let's say, 3.17438, whatever, right? I came up with this just out of my head. And the question is, did I really generate this randomly? And it is a really tough question because there's no way to verify. So I don't really know if this number came randomly to me, or would I have always written the same number? And there's another issue to randomness called the bias of small numbers. When we as humans think of a random number, we are very likely to choose a small number because the range of numbers is infinite. Let's say you build a random number generator and that operates for 2 years, generating a big sequence of random numbers. What I'm going to do is I'm going to take a real number line and I'm going to scale it such that the largest number you chose is just, kind of this range. And I'm going to argue that all the numbers that you chose were localized to this range and you ignored everything else in the space. Okay, so your choice was not really random. So we solve this problem by introducing limits. We say that the random numbers we generate should be between, let's say, 0 and some value. And once we do this, it's still not sure if the numbers that we can generate are truly random. But for this discussion, let's assume that it is. And we'll try to contrast this with the random numbers generated in computers. Okay, so are computers able to generate similarly random numbers? Because there are a lot of applications. Let's say you are simulating a game and you want to simulate the shuffling of a deck of cards. So I want to come up with some approach to be able to generate random numbers. But then a computer is a sequential machine. And these by design are predictable. What our mobile phones and computers do today seem random because there are billions of transistors inside of them and we are not able to predict the operations of each of them. But as a matter of fact, if all the variables in the current state is given to me, I could predict what the next state would be. Okay, so whatever process I use in a computer to generate a random number, that process is going to require some input, and for the same input, it's always going to produce the same output. Therefore, we say that computers are not able to generate truly random numbers, and the best they can do is to generate false or pseudo-random numbers. For example, computers today can track time at the scale of nanoseconds. And inside 1 single second, there are 10 to the power 9 nanoseconds. And since the system is able to track each of them precisely, anytime you want a random number, it's just going to choose what the current nanosecond value is. And that's going to be random enough for most practical purposes. And the idea is to be able to use some stochastic process that we cannot predict in advance. There are applications that allow you to move your mouse, for example, right? You move your mouse and it generates a random number based on your mouse movements. Okay, so enough said. For the context of our video, we look into one random number generator, and that's called the LCG, or the linear congruential generator. And this helps us generate pseudo-random numbers in computers. It needs 4 numbers to work with. One is called a seed value, denoted by x0. Then I have a multiplier, denoted by a, the increment c, and the modulus of m. Okay, and the rule is, in order to generate a term, you take the previous term. Okay, and then you multiply it with the multiplier, you add the increment, and then you take the modulus. How easy is that? And so far I've used 3 of these, and I need this to find the first element in order to be able to see it, right? Because this is a recurrence relation and this provides my base case. So this is exactly your formal definition. You could say a LCG is a random number generator that involves a seed, multiplier, increment, modulus, and defines a recurrence relation like this in order to generate every successive random number. That would be enough for a definition. So let's have a look at an example. Let's say I have x0 is equals to 27, a equals 17, c equals 43, and a modulus of 100. So my first random number would be 27 times 17, and I add 43 and take a modulus 100. Okay, and this is going to result to 2. And to get the next number, I follow the same rule. I use 2 as my seed, and each time I do that, it's going to give me a new number. So you can expect questions in your exams that ask you to generate, let's say, the first 5 random numbers using this approach. And I think you would be able to handle that easily. So before I close the video, I want to go over one little fact. What happens when I choose a equals 1 and c equals 1? And you'd see any term of mine, let's say xn, would just be 1 times the previous term, right? So that would be just xn minus 1, and then I'm choosing an increment of 1, okay? C equals 1. So if I start with a 1, it's going to give me a 2, and then a 3, and then a 4. So these numbers are not even random. The LCG is simply counting in this case. So the choices of the parameters A, C, and M determine the quality of the random numbers generated by this process. Okay, and there could be one more fact to observe here. The modulus that I'm taking is M, therefore the numbers that I generate would be in the range of 0 to M. But the linear generator could generate a shorter loop and not cover all numbers. For example, if I'm generating a modulus of 15, the LCG could say 1, and then 5, and then 9, and then 1 again. And if this happens, I'm just going to cycle between 1, 5, and 9 forever, okay? And even though my modulus is 15, I'm not going to cover all the remaining numbers. So there are different approaches on how to choose the parameters. We're not going to go into those as part of the video. It's already too long. But you can definitely find a reference how to optimize these things if you want to. And finally, most computers need to generate a random numbers between 0 and 1. And we do that process by simply dividing the generated number by the modulus, okay? So I'm generating a number between 0 to M. And if I divide by the factor M, I'm bound to get a number between 0 and 1. Okay, so that was the content for this video. In the next video, we'll be looking into the concepts of primes and coprimes, relative primes, the GCD, and the extended Euclidean algorithm. So I'll see you guys in the next video. Thank you for watching. Have a good day and bye.